Okay, so we're going to pick up on our study of the mechanics of rigid bodies in planar motion and take a look at angular momentum. All right, so we've already seen if we're in an inertial frame that Newton's second law can be applied to rotations to say that the net torque applied on something is equal to the time rate of change of its angular momentum. That's all well and good, but what if our object that we need to analyze, for which we need to analyze the torques, is also undergoing a translational acceleration? Then it's no longer in an inertial frame and we'll have to be more careful about it. So we'll go ahead and put that in as our origin there. And this is for our inertial frame. And actually, let's make this a different color here. We'll make this our origin for our non-inertial frame. Okay, so then if we want to look at some point, like so, we'll go ahead and call this O prime. In the unprimed frame, we would say that that point is at a position Ri. Similarly, in the primed frame, we would say it is at position Ri prime. And we'll tie the two together by letting R naught here be the vector that points from the origin of the inertial frame to the origin of the non-inertial frame. So with that as our startup, we can say, okay, then Ri would be equal to R naught plus Ri prime. And then to get the velocity, for instance, we would differentiate that once. So we'll get Vi equals V naught plus Vi prime. Okay, cool. So the force being applied onto this point I here, which is going to represent our ith particle, by the second law would be equal to ddt of mvi, and we'll go ahead, mivi, and we'll go ahead and assume that the mass is a constant like we always do. So we can pull that out. So it'll be mi, and then we need to differentiate vi. Well, that will give me a dv naught dt plus a dvi prime dt. Okay. So the torque that we measure in the primed frame would be equal to sum over I of Ri prime crossed with Fi. So that's going to be these positions crossed with the positions of these particles crossed into the forces being applied on those particles. And yes, that is Fi, not Fi prime, because we still have to work in an inertial frame. Alrighty then. So this will be equal to sum over I, Ri prime crossed with our Mi. Now we've got a V naught, V naught, no prime there, dot plus a Vi prime dot. All right. So they'll become expanded around. They'll get sum over I, Mi, Ri prime crossed with v naught dot plus sum over I mi r I prime cross vi prime. Okay, now here we're gonna take the identity that if we exchange the terms in cross product, so if we anti-commute the terms, we're going to pick up a minus sign here. So this will be minus v naught dot crossed with sum over I mi ri prime. And then here, I will be able to, I'll show in just a second that it'll be legit for me to move this differential all the way through. So d dt of sum over I mi ri prime cross vi prime. Now, why can I say that I can get away with that? So here's a little aside real quick. d dt of sum over I mi ri prime cross vi prime will equal, well, we have to go ahead and do the product rule, sum over I mi times, differentiating this will give me vi prime cross with that vi prime, plus then I'll have ri prime crossed with vi dot prime. And that term is 0 because the vectors are parallel, since it's the same vector. So basically I can just go ahead, add that v cross v in for free, and then write it like that. If I do that, I recognize that that, by definition, is d dt of the angular momentum measured in the primed frame. So what I get, after that aside is over, is that the torque measured in the accelerated frame is equal to minus r naught double dot, I just took my v naught dot and took it to r naught, crossed with, for reasons I'll become apparent in a moment, crossed with sum over I mi r I prime plus dl prime dt. Now that should be raising some alarm bells for you, because you've seen this before, whether you realize it or not. When you analyze, say, things like a ball rolling down an inclined plane in your lower division mechanics class, we went ahead and just blithely suppressed this whole term. And maybe something was barely mentioned about it, and maybe not. Well, it turns out that the cases that you generally look at in lower division physics fall into one of three cases, all of which will allow you to make this first troublesome term disappear. So we'll just say here, we'll call it term 1. So conditions to make term 1 go away. All right, one possibility here. Typically, this is sort of thing you'd be looking at if, say, you're looking at some sort of physical pendulum or something like that. So say something like that. You had the case where your v naught was a constant. So if, say, you were, analyzing some pendulum swinging while in a car moving at a constant speed, well, then that's okay. Because v naught is constant, that means that r double dot naught is equal to 0, and then term 1 goes away. All right, another possibility is if you put the axis at the center of mass, this is usually the axis for O prime at the center of mass. So for instance here, if we took a look at, say, a cylinder or a sphere rolling down an inclined plane, what we did was we always naturally enough, stuck our O prime at the center of mass. Now, the reason that that's okay is that in that case, we can rely on our favorite little trick, that's sum over I, MIR, I prime, in this case here. Well, that will be locating the center of mass with respect to the center of mass. And so then that is 0 in that frame, and that makes that go away. So that's the case of O prime at the center of mass. Then finally, possibility number 3. We looked at it a little bit when analyzing rolling without slipping down an inclined plane, say. So here, what you do is you go ahead and stick your axis, say, right here. There's your center of mass right there. Then let's say we're looking at something where this whole thing is just up and moving. If we are clever enough about it, we can, say, have it accelerating through the center of mass. Well, in that case there, our sum over I, M, I, R, I prime will equal M times R, C, M prime. That points at the center of mass. And so this is parallel or anti-parallel to that. So, this would be, in the way I got drawn here, this would be my RCM prime like that. So in that case there, I've got my acceleration of the system, say this whole thing's in a rocket accelerating that way. And it's either parallel or anti-parallel with this RCM prime. And then that's still okay because then that makes the cross product vanish. So we have that RCM is either parallel or anti-parallel to R naught double dot. All right. So it turns out that most problems that most people will ever give a rip about fall into one of these 3 categories, and so you're happy. And that's good, because otherwise, if you can't make this term go away by being clever, you're pretty much stuck with having to resort to doing finite element analysis, which is fine, but fire up the computers and be prepared for them to weep. Okay, in the next video, we will take more of a look at laminar motion.